Hello and welcome to our presentation on climate change. Students in the statistics class at Rainy River Community College have researched the types of data that are used to develop climate change models, and we also analyze data to determine how climate may be changing in our local area. This presentation has three parts. Part 1 introduces the connection between carbon dioxide and temperature and how these variables are predicted by statistical models. Part 2 examines several sources of data that are used to create statistical models for climate, including methods of data collection and potential sources of error. Finally, Part 3 is an analysis of historical temperature, precipitation, and water levels data for our region to show local effects of climate change. Part 1, Carbon dioxide and temperature. The greenhouse effect is what allows the planet Earth to have a ground temperature that supports life. As heat from the sun is reflected back to the atmosphere, a layer of gases that includes carbon dioxide, water vapor, methane, and nitrous oxide traps some of that heat. As the amounts of these gases increase in the atmosphere due to human activities such as combustion of fossil fuels, the amount of heat that is trapped also increases. Models show that this increase in temperature can affect weather patterns, including the timing and amount of precipitation, flooding, and droughts, as well as ocean chemistry and sea level, and patterns of survival and reproduction for living organisms.
Paleoclimate evidence is simply one in a number of independent lines of evidence indicating the strong likelihood that human influences on climate play a dominant role in the observed 20th century warming of the Earth's surface. Numerous studies suggest that the mean warmth for the late 20th century appears to exceed the warmth of any comparable length period over the past 1,000 years. There are numerous myths regarding the hockey stick reconstruction of past temperatures.
There was questionable reliability in taking the data for the hockey stick graph, which is shown looking at the graph.
The ocean also plays an effect on climate change. However, the ocean is not warming as fast as land climates just due to the sheer size and depth of the oceans. So oceans may slow down climate change, but it also makes it harder to reverse because as the ocean warming continues to happen, which will take a much longer period of time, it prevents land climates from cooling back down due to all the heat being released from the ocean. And there's a graph explaining changes in the global climate over time, and large numbers of models have been compiled in order to form different lines to predict, and there's around 4 different predictions, but all of them predict that there will be a steady increase. So how do they predict the future? Data gathered by climate scientists is entered into computers using various algorithms to create different models and outcomes for what may happen in the future. In order to make these models accurate and believable, scientists will use what is called hindcasting. Hindcasting is where they will take a model and use known events in the past and cause the computers to predict those events accurately. And so once they can do that with precision, they turn those models to then, with current data, predict the future. They use the assumption that if it can predict the past correctly, it can also predict the future correctly. And they also use a wide range of chemical and physical properties in our atmospheres, oceans, and landscapes in order to make these predictions.
Climate models can use grid cell size as a variable. They define the resolution of the model. Climate models may include a time step, the atmosphere, temporal or time, and spatial or position variables. Inaccuracies can come from using the wrong equations, which can be improved over time by testing these equations. Another issue with climate model simulations is that they usually can't reproduce the time and position variables, especially over smaller scales. Climate change models have been able to realistically reproduce the change in the average temperature of the Earth during the 1900s. Climate models published since 1973 have generally been good at projecting future climates. They are considered to be reasonably close to what has actually occurred, although they aren't perfect and are getting better over time. The blue line of the graph shows regression. The red line shows the moving average analysis. The red line, or average moving analysis, is more accurate.
Part 2. Data sources used in climate models.
One of the ways they check for changes in the climate is by using ground stations. Ground stations have a large array of instruments to gather a very wide variety of data. This is anything from temperature to air pressure to ocean level to wind speed, anything you could think of that occurs in the natural world. And they have computers that will monitor for any spikes, outliers, large changes in the environment around it. Location can play a key. As you see here, ground stations tend to be more remote, and some are large, but some are also very small. Addressing inaccuracies with data. As with any data, there can be errors with it causing it to be unreliable, potentially misleading. Locations and surroundings, as said previously, can affect the accuracy of data. If you have ground stations in a city or on a, say, maybe an airport runway, there can be certain changes that occur that wouldn't happen in the natural environment. So that can lead to potential inaccuracies with your data. And they're addressed by taking several actions, and they send data to the National Oceanic and Atmospheric Administration, or NOAA, for quality checks. They constantly calibrate and check instruments and sensors to make sure they accurately gather information.
The way radar works is it transmits a pulse of energy into the atmosphere, which then can target a signal. The only way it works is if there is a target present. If it's present, the signal becomes scattered into a smaller part of the energy pulse. This then is reflected to the radar. A radar can be sensitive when this happens. It is based on the wavelength. Energy that transmits longer wavelengths are better than smaller ones. Causes of false echoes happen when pulses are intercepted by vegetation and buildings, which ruin the return signal, which can change the information. When using radar, the operator can see any nearby ships or planes, where they are, how quickly they're traveling, and the direction they're heading. On the left, you see a typical radar, and then on the right, you see a radar that you would see on a ship. The word satellite means a smaller space-based object orbiting or looping around a larger object. There are three main groups that we use satellite. We put satellites in space to overcome the limits of Earth's geography. This helps us step outside our earthbound lives. If you want to send something like a TV broadcast from one side of the Earth to the other, there are three stages involved. First, there's the uplink, then goes through transponders and ending with the downlink. We tend to group satellites either according to the jobs they do or the orbits they follow. However, these are very closely related because the job a satellite does usually determines both how far away from Earth it needs to be, how fast it needs to move, and the orbit it must follow. These are just a couple pictures shown of satellites orbiting the Earth.
Tree rings are collected with an instrument called an increment borer. The borer extracts a strip of wood that goes to the center of the tree. When the strip comes out, you are able to count the rings on the strip of wood. Scientists want to ensure that the trees are in a location where humans haven't intended the forest. It's possible that the tree rings are less accurate than previously thought. On the left, you are able to see the growth of the tree rings, and on the right, you can see how they take a sample strip from the tree. Ice cores are cylinders of ice drilled from the ice sheets. The layers of ice cores correspond to years and seasons, with the youngest at the top and the oldest at the bottom of the core. Information from the gas bubbles trapped in the ice allows scientists to determine the amounts of carbon dioxide and other atmospheric gases through time. On the left is a sample of an ice core, and on the right is a researcher working with an ice core drill.
Sediment that comes from the bottom of the ocean can serve as a timeline of events for that body of water. The deeper the sediment is, the older it is. Around 55 million years ago, a large amount of CO2 entered the atmosphere, which caused the Earth's temperature to rise. Much of that CO2 was absorbed by the ocean. Under the new water conditions, many organisms couldn't survive. When these organisms died, their shells sunk into the water, leaving a trace of sediment on the ocean floor. The data can be collected from wash lobes by hammering sections of aluminum irrigation pipe. Scientists can cap the pipe and take it out of the water using ropes and jacks. The cores are split lengthwise in a lab, photographed and sectioned into 2-centimeter intervals for grain size analysis. Sediment in the tubes gets sieved and dried. Then there is a calculation for the weight percent, grain size distribution, and weight mean size. The picture on the left shows an example of an ocean sediment core, and the picture on the right shows where they store these cores. As corals grow, they form skeletons from the calcium carbonate in the ocean. The density of these skeletons change as the water conditions change, like water temperature, light, nutrients, etc. Corals that form in the summer are different than the ones that form in the winter. These changes give the corals growth rings, similar to tree rings. These rings can be studied to determine what climate was like during the seasons of coral growth. These rings allow scientists to date corals to the exact year and season, so it is an accurate method to use. Living corals can provide data of past climates from the past 100 to 500 years. The coral is collected by scientists in scuba gear that dive down to the coral reefs. They use drills to gather small coral samples from the coral without harming the coral. Scientists use X-rays to look at the coral's patterns. They mark the coral layers by years and season and extract samples of the individual coral layers for chemical analysis. Scientists can estimate the seasonal temperature and rainfall to create a record of how the climate has changed over time. If the environment changed with a disease breakout or the coral got bleached, those things can be shown by the bands or layers in the coral.
Part 3, Analysis of Local Climate Data. Temperature and precipitation data were obtained from Climate Data Online, a database provided by the U.S. National Oceanic and Atmospheric Administration. The zip code of International Falls, Minnesota, 56649 was used, resulting in data on high temperatures, low temperatures, and precipitation totals from 1948 to 2018. Water levels data were obtained from the National Water Information System, a database provided by the U.S. Geological Survey. 4 locations were selected in the region, and data was available from 1929 to 2018. Students used regression analysis to determine if there is a relationship between time and each climate variable, particularly to see if temperature, precipitation, or water levels have increased over time. Typically, this type of data would be analyzed with more complex statistical tests, such as time series, moving averages, or multivariable models. Linear regression is a fairly simple statistical analysis, but it was chosen because the students in this course learn how to calculate and interpret the results of this test. The p-value of a statistical test indicates significance. In these tests, the result is significant if the p-value is less than 0.05. Even though it is a simple test as compared to complex climate models, it provided some interesting results for our climate variables. High temperatures. High temperatures were analyzed 4 ways. Maximum high temperature of the year, the hottest day of summer. Minimum high temperature of the year, the coldest day of winter. Average or mean high temperature across the entire year, and the standard deviation, which is a measure of variation of high temperatures across each year.
For the highest high temperature of the year, when you look at the graph, we have a p-value of less than 0.05, so it's fair to say that we have a significant enough change to say that overall the highest high temperature recorded each year is decreasing over time. For the lowest high temperature of the year, or coldest day of the year, we can see that it is a significant enough change to say that over each year the mean is increasing. For the average high temperatures, we see that that is also increasing. And for the standard deviation, we see that the variation overall is decreasing. So our highest high temperature days are getting less common, and our lowest high temperature days are getting higher. So the variation between each of those is getting more and more narrow. So we are going to have less variation in our temperatures.
Low temperature. Low temperatures were analyzed 4 ways. Maximum low temperature of the year, the warmest night of summer. Minimum low temperature of the year, the coldest night of winter. Average or mean low temperature across the entire year. And the standard deviation, which is a measure of variation of low temperatures across each year.
The graph shows the highest low temperature of the year. The highest low temperature recorded each year has not changed significantly over time. The graph shows the lowest low temperature of the year. The lowest low temperature recorded each year has not changed significantly over time. The graph shows the mean low temperature of the year. The mean low temperature has increased over time. The graph shows a variation in low temperature over time. The variation in low temperature recorded each year has decreased.
Precipitation. Precipitation data was obtained in inches per day, where snowfall was converted to inches of water content. Precipitation was analyzed 2 ways. Total precipitation for the year and maximum precipitation for the largest daily precipitation amount for each year.
The graph shows that the total annual precipitation has not changed over time. This graph shows the single largest daily precipitation amount, and the maximum daily precipitation number has not changed over time.
Water flow. Water flow is a measure of how much water is passing through a sampling location per unit of time, in this case, cubic feet per second, or CFS. Water flow was analyzed 2 ways. Mean flow for the year, measured from ice out in the spring until the end of October each year, and peak flow, the highest recorded daily flow for each year. These 4 monitoring stations were chosen because they have the most data available in the region. Gold Portage Outlet has data back to the 1980s, while the Little Fork, Big Fork, and Rainy Rivers have data back to the 1920s.
On the left graph, you can see that the mean flow has increased over time. On the right graph, you can see that the peak flow has not changed significantly. On the left graph, you can see that the mean flow has not changed over time, and on the right, the peak flow has not changed significantly over time as well. On the left graph, you can see that the mean flow has not changed significantly, and on the right graph as well. On the left graph, the mean flow has not changed significantly, and on the right, the peak flow has not changed significantly as well.
In conclusion, for temperature, both high and low temperatures have a significantly increased over time in our local area. Mean high and mean low temperatures have each increased by 2 degrees Fahrenheit or 1.1 degrees Celsius since 1948. Even this small temperature change can influence things like growing season for agriculture, species for survival and reproduction, lake ice quality and duration for ice fishing, and high and low water events or floods and droughts. For water levels, the mean water flow has significantly increased at the Gold Portage outlet of Kabetogama. Other sites we tested has also increased, but the increase is not statistically significant. Peak flows have not changed for the 4 sites we tested for this project. This project was inspired by a request from a community climate action group to help people understand climate change and to have our final project coincide with Earth Day, April 22nd. We hope you learned as much as we did about how climate data is collected and used to create models, as well as the impacts climate change is already having in our region. If you would like to learn more about climate change in Minnesota, the Pollution Control Agency and the Department of Natural Resources both have educational websites on this topic. Thank you for watching and happy Earth Day.